So hi everyone. So I tried to keep the whole discussion simple to have it useful for a broad audience. For the people who are expert on statistics and statistical learning, I mean, don't hesitate to come and discuss with me afterward because I won't go into much details. So to begin with, here is an observation from the Herschel Spire instrument at 250 microns. Okay, it's around 2 degrees on the sky, okay? And you see a large structure here, which is the emission from our own galaxy. So nothing new for you. And if you zoom a bit, okay, you see a lot of small dot, bright blobs, okay, which are related to the emission of all the other galaxies in the universe. Basically what we call the cosmic infrared background. And you have also this diffuse background. And here in this image, so we have this combination of galactic dust emission and cosmic infrared background, sorry. And the cosmic infrared background can be seen as a contaminant, okay, if we want to study the galactic dust at small scales. So here the idea is, how can we do to study statistical properties of this galactic emission without being contaminated with the galactic cosmic infrared background? And actually, this kind of issue is kind of ubiquitous when you work with interstellar medium. I mean, you are all faced with that, so I won't enter the details. So you had this example of galactic dust emission and cosmic infrared background. If you try to work with galactic foregrounds for cosmic microwave background, you have a lot of different foregrounds that you try to characterize, to separate in particular between themselves and with the CMB. If you work with for radio data, for instance, we had the talk from Francis this morning. You have the cold and the warm neutral mediums media that you want to separate. I mean, and you have a lot of other examples like that. So if you want to do a component separation, you have different lever arms. You can use the difference of spectral properties between the different components. And we saw already a few talks on that, and we will see other talks. So I won't discuss that more. And you can also use the difference of spatial properties. So a lot of works exist when you try to work with the power spectrum, but as we will see, the power spectrum is not characterizing the spatial morphology, the structures that you see in the image. And Edith talk, for instance, about these kind of structures, which have a huge importance. And you can try to take into account the morphology, okay, to do this component separation. So, but then the question is, how can we rely on morphological features to make this component separation? And also, how can we have methods that could be directly applicable to astrophysical data? Because, for instance, when you speak about morphological features, there are a lot of new results with machine learning approaches and things like that, which are very promising. But I mean, you need to be able to apply that to observation if you want to really have at the end astrophysical result, and it can be very complicated, in particular when you don't have a proper physical models of the different components. So probably most of you know that, but so the power spectrum is, I mean, that's the first summary statistics that you want to study in a process, probably because it gives you the energy power in each Fourier mode at each scale, and it's very useful. But I mean, the power spectrum, per definition, is you can compute it as the square of the amplitude of the Fourier transform at each wave number, at each mode, okay? But when you do that, you treat each scale independently. So you don't have any information about the statistical dependencies between the different scales, okay? Which means that, in fact, you don't characterize the structure in your processes. And to give you an example, here you have two fields which have exactly the same power spectrum. I mean, I constructed the right one from the left one, so I can then show you they have exactly the same power spectrum, which means that if you try to compare them and you use only the power spectrum, this summary statistic will say to you that these fields are exactly the same, which is a huge problem, okay? And actually, when you have structure, it means that you have nonlinearities, okay? Typically in turbulence, you know that you have your V grad V term, if you want, and it will couple the different scales, which means that there will have some kind of interaction, some kind of statistical dependencies. And the idea is, how can we use these dependencies between the different scales as a lever arm to make the component separation? And that's exactly the different way, that's a different way of formulating the problem of how to use morphological information. So here in the for the rest of the talk, I'm speaking about spatial morphologies. I don't go into the spectral features anymore. I mean, at all. So if we come back to the problem of galactic dust emission and infrared, cosmic infrared background. So here you have the initial image that I showed, okay? And here you have another field in the sky, which is called the Lockman hole, where the galactic emission from the Milky Way can be mostly neglected, okay? And if you look at it, I mean, we can see that the galactic dust emission and the cosmic infrared background clearly have different coupling between scale, different morphological structures, if you want. And actually, we could be able to use this information to make the component separation. Here, if you look at it, so you have some galaxies which are resolved. It's related to small blobs. And here, if you filter the field at different scale, you will have some bump of amplitude, if you want, at different scales. There is a statistical dependency between this bump of amplitude, which means that here, at the smallest scale, is the CIB, which is dominating. But basically, if you ask yourself, okay, at intermediate scale, if I see a bump of amplitude, is it related to the CIB or is it related to the galactic dust emission? You can look at the smaller scale. And if at the smaller scale, you have a lot of energy at this position, you can infer that probably what you see at intermediate scale is related to the CIB. If it's not the case, maybe it's rather related to the galactic dust emission. And you have the same ideas when you go to large scale to small scale. Here, you see that you have a huge filamentary structure related to the galactic emission. And if you see this kind of, if you see some local amplitude, which is a bit higher, okay, but located on this large filamentary structure, you can have an information that, okay, if it's statistically dependent with what you have at large scale, it's probably related to the galactic emission. So that's this kind of information that we want to use, okay? And so we'll ask the question, how can we take into account this interaction between scales? So basically, in the 8 minutes I have left, I will try to convince you that we can do things with scattering transforms that I will introduce. So scattering transform statistics are a set of summary statistics, family of summary statistics, which have been initially developed in data science, and then which have been introduced in various natural science, in particular in astrophysics. So basically, it's inspired from neural network, okay? But it's only summary statistics. So the idea at the time was to try to understand why the neural networks were working so well, in particular with comparison to usual higher order summary statistics, and try to inspire ourselves from this neural network to build new efficient set of summary statistics. Okay, so due to that, they have an efficient characterization, they have a low variance, you can estimate them only on a very small amount of data, which is good. And they don't need any training stage, that's summary statistics. So you have an explicit mathematical form, you can write them on a paper if you want. And so you can try to interpret what they mean. And the broad idea is that you have an initial image like that, and you will basically separate its information over its different scales. And then, so to do that, you will use wavelet filters, which are basically just simple bandpass filters. And then you will characterize this coupling, this interaction between scales with nonlinearities. So let's consider again the initial fields that we had, okay? Here, you see it, that the Herschel spire observation. And basically what you can do is to filter it with bandpass filters, which are wavelets, okay? So they are complex wavelets. So when you do the convolution, you have the local amplitude of the oscillation and the local phase of the oscillation. So here, let's say you have a vertical 8-pixel oscillation, and here a vertical 16-pixel oscillation. You see the local amplitudes, as we said, and if you take the phase, you have the local phase. So it oscillates in average at here 8 pixel and here 16 pixel, but you have also some features which relate to the local structure and the initial image, either at 8 pixel or 16 pixels. And basically, if you want to characterize this structure, what you want to do is to see, okay, do we have, for instance, a phase alignment? And indeed, you see that you have information about this phase alignment. Here you have a huge structure, and you see it in the phase here, and even this diagonal filamentary structure, you can see it in the phase here and here. And you can also look at the amplitude. Here you have the local amplitude, and you can see it, okay? So how can you characterize this interaction? So basically, if you take covariances, the problem is that it will be 0, because it's like integrating cos x, cos 2x. That's the ideal example of processes which are dependent, but that's linearly decorrelated. But what you can do is introduce nonlinearities. For instance, you can multiply the phase by 2 here. And here you have a phase that oscillates at 8 pixels, but that is related to what was in the initial image at 16 pixels, okay? So then you do a correlation and you have an information about the fact that the scales are statistically aligned, anti-aligned, or independent in terms of phase. And you can do the same, for instance, if you take the amplitude, you have the local correlation, the correlation between the local amplitude of the oscillation at different scales, okay? Doing that, you see that you have summary statistics. Here you have one coefficient by pair of scale by type of interaction. So actually, there are a lot of, it's a family of statistics. I won't enter in the details. You have wavelet scattering transform, phase harmonics, scattering covariance spectra. They all share the same framework. And what is nice is that they have been used for characterization and parameter inference for a lot of very different processes. And at each time, they were able to reach or go beyond state of the art, to be very informative. And basically, that was the same statistics which have been applied to all these processes, which means that they are actually quite general. So one huge advantage of this statistic is that you can build scattering generative model from them. So basically, it means that you have a set of statistics that you estimate from one map, for instance, and then in the maximum entropy framework, which relates to the information theory that Emmerich spoke about, you can build a generative model that allow you to sample new maps, okay, which approximates the initial process. So to give you an idea from a practical implementation, so you can compute statistics that I will call phi, and then you can sample, in a particular case, you can sample, in a specific framework, you can sample new realization with a pixel space gradient descent. You start from a white noise, and you do a gradient descent in pixel space in order to have a final map which has the same statistics. And you can do that as much as you want by starting with new realization of the white noise, okay? So here to give you an idea, that's the kind of samples that we can have from one single image. So we estimate the statistic from all these images, and we're able to sample new realization as much as we want. So here you have example of the realization which can be sampled from these single images, okay? So this is an example of what can be done. And then as soon as we have that, okay, we have an ability to characterize very quantitatively the kind of structures that we see in the image. How can we use this information to make component separation? So we come back to the initial image, to the initial problem, CIB galactic dust. So here we treat the left image, just I simplify the whole thing, but as a sum of the galactic dust emission, S, and the contamination, here the cosmic infrared background, C, okay? So we have this independent CIB observation. So how can we use the difference of morphologies to make the component separation? And then what we can do is to try to write some kind of constraints in the same way that we wrote this previous constraint with components with generative model and use it to generate a new map, okay, that is compatible with the data and the kind of information that we have, the kind of constraints that we have. So first we have a map from the CIB. So we have the information about the structure of the CIB. So we can estimate scattering statistic on this map, and we can also build, okay, a model of the CIB and generate as many CIB map as we want. I don't have them here, but I mean, I could show them to you. It looks typically like the map to the right, okay? And then what we can do is they can generate a new map, S-TIL, which will be the separated dust map, if you want, with a gradient descent in pixel space. And here we have several constraints. I know that if to this galactic emission map, I add other relation of the CIB, it should be statistically compatible with the left data, with the total data here. And it should be the case whatever the realization of the CIB is, okay? And I know that also the components that I could identify, that I will identify as CIB, C tilde, which is data minus what is the galactic dust, should be compatible with CIB. So I can write this kind of constraint, do the gradient descent, and that's typically the result that I get, okay? So here you have the total data. Here what I identify, what is algorithm identified as the galactic dust emission, and here as the algorithm, what the algorithm identified as the CIB, cosmic infrared background, okay? So basically it shows that we were able to make this component separation at a single electromagnetic frequency and relying uniquely, solely from observation data. We only use the two previous images that I showed to you before, okay? And with some validation scheme using alternative observation data, we use that, we expect the galactic dust properties to be recovered statistically up to the Herschel beam, okay? So to conclude, So we have scattering transform, which are efficient on Gaussian statistics inspired from neural network, but they can characterize, so they are summary statistics, but they can characterize interaction between scale in nonlinear interstellar medium processes. Okay, you can have new efficient covalent separation algorithm, which are able to leverage the difference between the morphological differences between processes. And I showed to you, I hope that it can work even with a very limited amount of data. And actually, I showed you only one example of covalent separation, but it's a very flexible and versatile algorithm. So we apply it to different things. You can use ancillary data if you want, and so on. And also, you have this kind of generative model with scattering transforms. So they are low-dimensional parameterized models, and they can be combined with other approaches. If you have machine learning algorithm and you need some generative model which are parameterized, even if you don't have especially physically driven prior model, you can use this algorithm. And there are some work to do that. We work, which worked quite well. So we'll continue to work on that. So thanks for your attention, and don't hesitate to come and discuss if you have questions.